Welcome to Lesson 3E, Area Ratio versus Mach Number Relationship. In this lesson, we'll derive the area ratio versus Mach number relationship for our standard conditions. Then I'll discuss several solution methods for how to solve the resulting equation, which is implicit when you want to find Mach number at a known area ratio. I'll do this with an example problem. First, let's derive the relationship. From a previous lesson, we had these two mass flow rate equations. The first one is a general case and applies whether the flow is choked or not. The second one is for the choked case, where back pressure is low enough to have choked conditions or sonic flow at the exit. And we're talking again about this familiar converging duct. Let's consider the choked case. Both of these equations are valid, so let's just equate them. And these equations apply anywhere in the duct, in other words, at any area. When we equate them, we get one big equation. This is the first equation, and we set that equal to the second equation, as shown. This term on the left and this term on the right are the same, so those can cancel. Likewise, P0 appears on both sides of the equation and cancels. Before I continue, I'll make a very important comment. Namely, P0 and T0 have canceled out. This implies that our equation is valid for any upstream stagnation conditions. To continue this derivation, I'll leave A on the left and divide by A star. From the right, I'll put everything else on the right side. I get 1 over M, and let's rewrite this as 2 over gamma plus 1, the reciprocal, so that I can get rid of the negative sign. I get gamma plus 1 over 2 gamma minus 1, and I put that here, 2 over gamma plus 1 to the exponent without the negative sign. And then this term, which I'll copy and paste to save me some work, but since I moved it to the right side, I get rid of this negative sign. Now notice that the exponents are the same, so we can combine these two terms under the same exponent. And our final equation is thus A over A star is 1 over Mach number, quantity 2 over gamma plus 1, 1 plus gamma minus 1 over 2 m squared, closed quantity. The exponent is gamma plus 1 over 2 gamma minus 1, but we don't need these parentheses up here. This is our final equation. I'll put lots of stars around it, and I'll call it equation 1. This is called the area ratio versus Mach number relationship, and of course it's valid for an ideal gas only. We're also assuming adiabatic isentropic one-dimensional duct flow. I'll make a comment which is similar to what we've seen before for stagnation properties and for critical properties. Namely, this equation applies even if A star does not exist anywhere in the flow. In other words, even if the flow is not choked. You can also do a quick verification. When m equal 1, A over A star is 1 over 1, 2 over gamma plus 1, 1 plus gamma minus 1 over 2 times 1 squared, or 1, to the gamma plus 1 over 2 gamma minus 1. And if you do the math here, everything in brackets turns out to be 1, and 1 to the anything is 1, so A over A star equal 1, which is what we would expect when Mach number equal 1, because by definition A is equal to A star there. So this is a good check. Now let's do an example problem. Here's our area ratio versus Mach number relationship, which I typed up, and I point out that this equation is explicit. If Mach number is known, you just plug in Mach number and gamma and you can get A over A star. But this equation is implicit if you want to solve the other way around. For a known value of A over A star, how do you get M? You can try solving for M from this equation, but good luck. I haven't been able to do that. So let's discuss various ways to solve for Mach number M at a given value of A over A star. First, I'll show an explicit example. Namely, let's pick a Mach number. I'll pick Mach number is 0.43026, and the gas is air, where gamma is 1.40. You plug in this equation, and it's rather easy to do because you just plug in m and gamma, and you get a over a star is 1.500. Now let's try this implicitly. In other words, let's do this backwards. If we know a over a star is 1.500, we want to calculate the m, the Mach number, that gives us this value. Well, I know my answer is going to be 0.43026, but suppose I didn't know that. How would I get this? Also, because of the squared term that's here and the nature of this equation, there are two roots for a given a over a star. It turns out that there's a subsonic root and a supersonic root, and here we're interested only in the subsonic one. Well, let me ask the students, how would you solve this equation implicitly? I'll list these techniques as the students say them.
My calculator can solve equations like that, dude.
That's nice, Joe, if you needed to do it just a few times, but it can get cumbersome if you have to repeat it for many values of a.
I'd probably just use trial and error.
That works too, Harry, but what if you had to do it for, say, 50 values of a over a star? This could take a lot of time.
I would plot a over a star versus Mach number, and then zoom in the plot to see which value of Mach number crosses the desired a over a star.
Graphical analysis would work, BJ. You simply plot a over a star versus Mach number. If this is 1, you'll find that it has a minimum at 1 and then goes up again, and at a given value of a over a star, for example 1.50, you get two roots. One is subsonic and one is supersonic. Again, that works, but you'd have to have a lot of resolution on your plot to get at least 3 significant digits.
I would probably just search for an app or a website that did the calculations for me, 'cause I ain't so great in math.
An app or a website also is good, Dud. In fact, I'll show you a cool one right now. Here's a good example website. Here's the URL, and I'll add a QR code so you don't have to type it in. Here's the default values, 1.4 for gamma, so let's keep that. And for the isentropic flow relations, we'll pick the subsonic a over a star. I'll set this to 1.5 and hit calculate. And there's my answer, 0.43026. We also get lots of other properties. We'll use this later in the course as well for normal shock relations, oblique shock relations, Fano flow, and Rayleigh flow. I like to use this to test some of my answers, but I prefer to use my own software.
I would use the solve features in MATLAB to find the roots.
That's a great suggestion, Boris. Once you have it set up, you could create a do loop to calculate m for any number of values of a over a star. I'll list some other methods. In the old days, we used tables. You can still find tables that show a over a star as a function of Mach number. Here's an example from my fluids book, remembering that we use MA in the fluids book instead of M, but the table is still valid. When I was in school, we didn't have calculators yet, and we had to use tables like this and interpolate. You can also use the goal-seek or what-if analysis in Excel. There's also something called the false position method, which is kind of like a fancy trial and error method where you interpolate to find your next guess. And there's also something called Newton's method, which some of you may have used in other courses. I'll briefly explain the false position method. You set up your first guess, where we're guessing Mach number, say we guess 0.3, then we calculate a over a star from our equation 1. That's the value I got. I'll pick 0.7 as my next guess. I get 1.0944. If you're really lucky, you'll guess the right m that gives you 1.5. But we weren't that lucky. So now I interpolate with the goal of getting 1.5, and you should all remember linear interpolation. This value is 0.7, the lower one, our second guess, plus 1.50 minus 1.0944, this value, divided by the top value minus the bottom value, this minus this, times the difference between these two. And the trick is to always go in the same direction. top to bottom here, top to bottom here, and top to bottom here. This gives me 0.52752, which I now use as my third guess, and my A over A star becomes 1.2906. Then you just fill down these two cells. In Excel, I converged everything to about 6 digits in 7 or 8 iterations. This is the subsonic root. If I make supersonic guesses like 1 and 2, I get 1.85412, which is the supersonic root. I also have a short video on the false position method, and I show a QR code here for that. I'll also briefly mention Newton's method. It's similar to the false position method, except we use the actual slope to get our next guess instead of linear interpolation. Here's how Newton's method works. For some function g of m, we pick g such that g of m is 0 when m is a correct root. Here's the procedure. You guess m, you calculate g of m, you calculate g prime of m, you calculate a new guess, namely m new is m old, the previous guess, minus g over g prime. And then you repeat until g of m goes to 0, or to something very small like 10 to the minus 10th. Here, from equation 1, we want to create our g so that it's 0 at the correct m. And you can see that all I did was replace the equal sign in equation 1 with the negative sign, so this equation should be exactly 0 at the correct m, keeping in mind that there are two correct roots, a subsonic one and a supersonic one. If we guess a subsonic m, we should get the subsonic root, and if we guess a supersonic m, we should get the supersonic root. Well, the problem with this method is that you also have to calculate g prime. I'll start it for you. A over A star is known, and it's a constant, so the derivative is 0. And then we have to use the product rule on this guy. I'll differentiate this one first. This gives us minus 1 over m squared, times all this stuff in brackets and exponent, which I copied and pasted. Then I treat this one as a constant, and take the derivative of this whole thing in brackets. That is, the exponent times that expression in brackets again, minus 1 from our calculus class. We're not done yet. Now you need to take the derivative of everything in brackets with respect to m. I'll leave the rest as a homework assignment. But once we have this expression for g prime, we can start our iteration process using g and g prime with the procedure I showed you. I programmed this into Excel, and we get our two roots. The subsonic one is the same value we had before, and the supersonic one is also the same one we had before. So these all agree, which makes us happy. I'll show these last three in Excel. Here's an Excel spreadsheet that I created to show these various methods of calculation. I set my gamma, and then I pick an A and an A star so that the ratio of them is the desired 1.5. I'll show the goal-seek method first. This is my Mach number that I guess, and this is the equation for A over A star. You can see that here as well. Excel has a built-in what-if analysis and goal-seek. I'll show you how to use that. You go up to Data, What-if Analysis, Goal-seek. I'll move this out of the way. We want to set this cell to our goal of 1.5 by changing cell, this one, which is wrong right now, and then we hit OK. It iterates for a while and gets pretty close to the value that we want. I hit OK. I find that goal-seek is accurate only to about 4 digits, which is usually good enough. Now let's look at the false position method. You need to give two guesses, and again this is just the A over A star relationship as a function of Mach number to the left, and gamma is fixed, hence these dollar signs. So these are our first two guesses, and then from here I interpolate between these two and these two to try to get to my goal, which is 1.5. I calculate A over A star for there, and then from here on I can fill down because I'm always taking the last two. Here, for example, I'm interpolating between these two values and these two values, trying to get A over A star to be 1.5. You can see that after a number of iterations, it converges, actually to machine accuracy. And we get 0.43026 like we want. You don't even have to be real close. Suppose I pick 0.6 and 0.7. It still converges. Or I pick 0.7 and 0.8. Well, in that case, it went to the supersonic value. So I'll have to go back down here to get my correct value. So the initial guesses are important for getting the correct answer. I also show the supersonic case, which we'll discuss later. I pick 2 and 3 as my two guesses, and I get 1.854 as my Mach number that gives me the proper A over A star. Again, this is not very sensitive. Suppose I picked 3 and 4. It still works. As a final verification, I put in the subsonic and the supersonic roots, and indeed I get my A over A star, where this is just our equation all over again. Here's Newton's method. In this case, I have my goal. I make my initial guess, and this refers to a cell that's way to the right because I did all my iterations horizontally. I have my equation for G, my equation for G prime, and then I calculate a new M. I just duplicated those for many different iterations until finally it converges. And I did too many iterations just to make sure. And this final M is the last iteration. I did the same for the supersonic case. Again, this converges very nicely, and you could change the initial guess, and it still does a really good job. Let's try 0.8. Well, that one didn't work. So you got to be a little bit careful. 0.7 gives us the correct answer. Same thing for the supersonic case, which we'll talk about later. And again, I verified these. As a final comment, you're welcome to try all of these or use any of these you want, but I've had the most success with the false position method, and I've used it over the years to solve many implicit equations. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.